Hello, my name is Jesse, and welcome to the second video in a series in which we recreate the classic game of Pong using modern tools. In the last video, we set up a build system and created a window. In this video, we will be focusing on the ball in the game, how it will be drawn, as well as how it moves. We will also be setting up a testing framework using the Catch library, which is a well-known and highly regarded testing framework for C++. Let's get started with drawing a ball to the screen. The SFML library contains a circle shape class which we can use to draw circles. Let's create an instance and see what it looks like. The circle shape constructor takes a radius and a point count, but the point count has a default value, so we'll ignore that for now and just create the circle shape with a given radius. We will define a constant for the radius as 20. And while we're defining a constant, let's take this time to add constants for some of the other magic numbers in the app. I'm going to use 1280 by 720 because it is a well-known aspect ratio. We need to set the ball's full color because SFML will set the full color to white, and that will prevent us from seeing the ball on the screen. We'll set it to black for now. The window object will allow us to draw the ball to the screen with its draw method. With that added, let's see what the game looks like. In the run terminal, let's call make and run the app. That's the ball alright, but something looks wrong to me. SFML initializes the circle's position to 0, 0. So why can't we see the entire ball and not just a segment of it?
Let's take a step back. Imagine an XY plane, like many would remember from high school maths. Let's make the Y-axis extend downwards and the X-axis to the right. This matches the coordinate system used in SFML. Now let's draw a shape on this plane. This is a bit of a simplification, but when SFML creates a shape, it creates a box around it. This is called its local bounds. The box uses a point called the origin to help with performing transformations. When we move, rotate, or scale the shape, we are doing this relative to the origin. When the shape is created, SFML sets the origin to the top left corner of the box. It's important to understand that the location of the origin is not the location of the shape. Changing the origin does not change the location, but it does affect the way the shape is drawn. Let's set up the scene as it is in our game. Our ball has a location of 0, 0, with its origin at 0, 0. When we render a frame, we see the entire ball in the top left corner of our window. The radius of the ball in this scene is 1, so let's set the origin to 1, 1. This places the origin in the center of the ball. When we change the ball's location now, the location we give it will be the center of the ball.
Now that we understand how a shape's origin works, let's set the origin of the ball to be at the center. We can do this by setting the origin to the value of the ball's radius. When we run the app, we see a segment of the ball in the top left corner. A simple formula for the motion of an object is new position equals current position plus speed multiplied by time. I'm going to set the ball's initial position to the middle of the window. Knowing this formula, let's get the ball moving along the x-axis. We will use a speed of 1 unit per second, and we use 0.016 as the time value because it is approximately how long one frame will take to run. Later on we will change this to use a more accurate frame timer. Let's add some comments to the game loop indicating what we're actually doing in it. We start with the event handling. We then update the game state. Finally, we draw the game. With all this in place, the ball should be moving across the screen. Let's download Catch, which is the excellent unit testing library I mentioned. We can search for it, and the project's GitHub page should be the first entry in the results. When I was making this video, Catch was transitioning from version 2 to version 3. We'll use version 2, and we can find the Go to version 2 branch link in the project README. Catch version 2 is a single header library and can be downloaded using the link on this README page. We're going to be using test-driven development, TDD, to help implement the functionality of the game. I'm going to create a testing framework library that will use Catch for its testing infrastructure and assertions. Later on, we may add a mocking library if we ever need that functionality. Let's define the testing framework by first creating a testing framework directory and then creating a CMake lists file for the directory. Within the testing framework folder, let's create an include directory with another folder with the same name as the library. The convention of creating a folder with the same name as your library inside the include directory of your library makes it easier to know which library an included file came from. We will see what this looks like later when we use this testing framework library. We can move the Catch header that we downloaded into the testing framework's include directory. Now we define the testing framework library in CMake by using the add library command. We define the testing framework library as an interface library because it does not contain any CPV files that require compiling. We also need to tell users of this library that they have access to the include directory we created. Lastly, we need to add the testing framework subdirectory to the project CMake lists file. Some of the functionality within the game does not use the SFML library. If at some stage we decide to change from SFML to another graphics library, we should be able to do that without changing any of that code. SFML is helping us with user inputs as well as drawing, but the game state should not have to be implemented using SFML. To achieve this, we begin by creating a new subproject, which we will call Engine. Engine will contain all the game state functionality. Before we start adding details to the Engine CMake lists file, let's include the Engine subdirectory within the topmost CMake lists file. Let's define the Engine library by adding it as an interface library. Engine doesn't contain any compiled files yet, so we'll leave this as interface until we need to change it. We're going to be unit testing Engine, so let's add a test folder and define a unit test executable which will contain the tests. Within the test CMake lists file, we will create an executable called Engine Unit Tests. We will also need to link the testing framework that we defined earlier to the Engine Unit Test executable by using the target link libraries command. Leave a comment if you would like to know more about CMake and why we use private in this command. Before we start adding tests to the Engine Unit Test executable, we need to add the test directory as a subdirectory in Engine CMake list. Let's now complete creating the Engine Unit Test executable by creating the test main.cpp file. Normally, to create an executable, you have to define an entry point using a main function. The catch library requires some initialization to be done and simplifies things by allowing us to let it define the main function. To do this, we define the symbol catch config main before including the catch header. We can now build the project and run the unit test app. To run the engine unit test, we first need to navigate to its output directory. When we run the test app, we see no tests run, which is correct because we haven't written down any tests yet. But we know the test app is working correctly and we can begin writing some tests now. I would like a class that would be responsible for updating the ball's position and dealing with collisions with pedals and walls. I think this class should be called Ball Dynamics. Let's create a test balldynamics.cpp file in which we will test the functionality of that class. Let's not forget to add the file to the CMake list as well. Before we can write any tests, we need to include the catch header from the testing framework. We can now create the first test case. Since we are practicing test-driven development, we begin with a failing test. Let's instantiate an instance of the class that we want to implement. If we try to compile this now, it would fail because we haven't defined the ball dynamics class yet, which makes it a failing test. To make the test pass, let's define the ball dynamics class. We'll implement the ball dynamics class in this file for now and move it to the engine library later. I don't want the ball dynamics class to have to know about the SFML types such as circle shape. I'm going to create a test shape class that I will use in place of any SFML shape types. The test shape class will need methods to set and get position just like SFML circle shape class does. However, SFML uses a two-component vector of floats to represent position. Our test shape should work with the same kind of data. So let's create a vector type for that position. Let's not worry about what type X and Y will be and just use a template for them. Let's use the test vector inside of test shape to store its position and implement the get and set position methods. You may be wondering why I'm using all these templates. We know SFML uses floats to represent position and that we can draw the ball with a circle shape instance. But the ball dynamics doesn't need to know about those details. We can implement ball dynamics in such a way that it will work with SFML and its floats, or a different rendering library that uses doubles. Let's start making some assertions. We'll create a test shape instance called ball, and we'll use floats as the type for the coordinates. I'm going to set the ball's position to 0, 0. We know that in the game loop, after every frame, a certain amount of time would have passed. We can use that time to update the entities in the game. Let's create an update method in the ball dynamics class. When we call update, we would expect the ball to be moved to a new position. Earlier we used an equation for motion that used velocity. We will need that here as well. Let's add a setVelocity method to the ball dynamics class, which it can use to update the ball's position. We'll start simply and set the x velocity to 2 and the y velocity to 0. Let's add this method to the ball dynamics class. I would like the types for the x and y velocity to be the same as the types used in the shape's position. In order to be able to know what types are used in position, we are going to need to know about what type of shape is being used. We can give ball dynamics that information via a template parameter. Now we need to get the type used in shape's position. We'll store that type as a number type. To reiterate what I just did, I'm storing the type that the vector, which shape returns from getPosition, uses for the x field as number type. With number type defined, we can use it to create the setVelocity method. I need to also specify the template in the ball dynamics instance. Because I'm using TDD, I'm not going to implement anything until we have a failing test. Let's test that when we call update with a time of 1 second, that the ball is moved to the correct position. Focusing on only the x values, the ball is at position 0, velocity is 2, and time is 1. From that equation of motion, we know that new position equals current position plus velocity multiplied by time. So we should expect the ball's x position to be 2. Catch allows us to place checks in our code using the require macro. With all that in place, we can build and run our tests. Our test is failing, which is great. It would be weird if the ball's position had changed without having any code to change it. The test is reporting that the ball's x position is still at 0 after calling update, which is what we expected. It is important when first getting started with TDD to always see your tests fail. With a failing test in place, let's make it pass. In order for the ball dynamics class to update the position of the ball, it is going to need a reference of the ball to use. We can send the ball shape to ball dynamics via its constructor. I personally prefer trailing underscores for private class fields. Let's pass in the ball. Now let's move the ball so that the test passes. The simplest code we could write is just setting the ball's x position to the value 2. Let's run the test. Our tests pass, but this is obviously not what we want. If anyone is not familiar with test-driven development, it consists of 3 steps. The first step is to write a failing test, and failing to compile is considered a failing test. The second step is to write only enough code that will cause the test to pass, committing any sins necessary to get it working, like returning 2 instead of calculating the value. Lastly, in step 3, we refactor and clean our code. With our test in place, we can clean and change our code without worrying if we are breaking any functionality. It isn't necessary to perform the refactor step every time. You can go quite a few iterations of writing failing tests and making them pass before you decide that it's time to refactor. For this tutorial, I'm doing things as slow as possible so that everyone can follow along. So I've just made the test pass. We can refactor now. One thing I don't like in my code is code repetition and magic numbers. Also, before anyone comments, we can't help but have magic numbers in the test code because that's the data for the test. The 2 is repeated from the value we assign to the x velocity in our test. We can get rid of the value 2 in the update method by using the value given to us in setVelocity. Let's create a field for the x velocity and update its value in the setVelocity method. Let's run the tests. We haven't broken anything and were able to remove the duplicated code. Now obviously, what I've done so far is not the correct implementation. I took a shortcut, and by taking shortcuts it will force me to write more tests which will ensure that the implementation is correct. Let's start again at step 1. What can we add to the test that will make it fail? Currently, I'm testing the update with a time of 1 second. If I split that second into 2 half seconds, I would cause the test to fail. Let's run the test again. The test fails and shows us that the assertion made at line 55 is failing. This is the assertion that the ball's x position is 1 after the first half-second update. Making this pass is easy if we just multiply the velocity by the time that we pass into the update method. Running the test again, we see that it's still failing, but now at a different point. It's failing at the second assertion, after the second update call. This is because we're not considering the current position when calculating the new position. Making this test pass is simple because we only need to add the current x position to the calculation. When I run the tests now, it's passing. I'm going to extend this implementation to the y-axis by performing the same process again, but this time using the y values. I'm happy with this implementation for now. I'm going to extract the ball dynamics class from this file and place it in its own file within the engine library. Let's create a file for this class inside the engine subproject. Now we can move the code from the test to its own file. We need to add header guards in our file and add any missing includes. There are a few changes we need to make to the CMake lists to complete the extraction. We need to add the include directory to the engine library. Link the engine library to the engine unit test executable. And lastly, include the header to the ball dynamics class in the test file. With all that done, the ball dynamics has been extracted from the test file into its own file, and the engine library is starting to get fleshed out. Let's run our tests and make sure everything is still working. To use the code we have in the engine library in the game, we need to add the engine library to the Pong app in the CMake list file. With that done, I can include the ball dynamics file in the main.cpp and use it. I need to set the velocity as well. I'm going to go with 2 to the right and 1 down. With that in place, I can remove this old code and call balldynamics.update. I'll use 0.016 as the update time again. Let's see what this looks like. As I said earlier, I want the balldynamics class to not care about what shape is used. And to prove this, I'm going to make the ball a square using the rectangle shape from SFML. We haven't changed the balldynamics class, but we have changed the shape it works with. Let's try to run it and see what happens. It just works, and that was the goal all along, to be able to separate the rendering code from the game state code. All that's left to do now is to commit our changes. Thank you for watching all the way to the end. Whether you like or dislike this video, let me know your thoughts and opinions in the comment section. That's all for me for this video. Goodbye and continue creating stuff.